So essentially what we'll be going over is Bayes' theorem, likelihood ratios, subjective probability and elicitation, risk attitudes, and everything that has to do with utility. Just a brief run over everything that is going to be covered in the quiz. So just I know some of you were here when I explained about likelihood ratios in Bayes' theorem, so I'm not going to go over that too much. I just want to reiterate the difference between events and outcomes. So events, the way I like to think about it is basically it's a thing that happens, right? An event, something that has occurred, like a volcano eruption, or based I'm not sure if you saw this in the module videos, but Dr. Reed gave the example of a king and the probability of the event of a king walking into a room and the observation that the king is a man. So the event is essentially the king walks into the room, right? And the outcome is that the king is a man, because an outcome is an observation that is caused by the thing that happens. So an outcome basically it's difficult to assess the probability of an outcome, purely an outcome, like as in PO. It's easy to assess PO given E, probability of an outcome given an event, because an outcome is usually contingent upon the occurrence of an event. So this is why we use Bayes' theorem. This is why we use likelihood ratios. This is why we have the notion of conditional probability at all. So at any time, if you feel like I'm going too fast, or if you would like me to slow down, or if you have questions, please raise your hand or unmute. So I'm just going to move forward. These are the 4 basic rules, essentially, of probability that will be important once you start working on Bayes' theorem and also likelihood ratios. In particular, this one right here, partitioning. And this partitioning rule also applies to conditional probabilities of outcomes. So I'll go over this in a little bit once we start the example, but I just want to mention that partitioning, which is basically saying that, so partitioning, if you have a sample space, right, A, and if you're cutting it up, A1, A2, A3, A4, and so on, the probability of A should be 1, and so on. That's partitioning. And this applies to conditional probabilities of outcomes as well. And we'll see why in a little bit. This is just Bayes' theorem. And really why Bayes' theorem is important is because Bayes is the probability of an outcome. Probability of an event given an outcome. This is something that we cannot observe. You can't observe this, typically. That's why we must calculate it with Bayes' theorem. This is observable. This is readily observable. And this is observable given enough data or enough repetition. Right? So, everyone clear about Bayes? All right, we're going to go ahead. So, likelihood ratios essentially is there are 3 separate terms that are confusing, but I want to emphasize that there are 2 different likelihood ratios here. Likelihood ratio LR sub 0 and LR sub n. LR sub 0 is related to the event. and LR sub n is related to the outcome. So the most important thing when faced with a question like this is to determine which one is the event and which one is the outcome. Typically, it's hard, but once you get the hang of it, it kind of becomes obvious, because usually they will give you the probability of an event. You have to have one probability of an event in the question to even begin working on it. And then you have something that's a little more confusing, which is the conditional likelihood ratio. And this is basically the conditional likelihood ratio of an outcome given an event. So it's the ratio of an outcome given an event and divided by the outcome given the event not occurring or not the event. So this is also, there's also CLRJ. The probability of not that outcome given an event and the probability of not that outcome given not the event. So if this doesn't make sense now, it'll make sense in a little bit, don't worry. And I know that Dr. Reed talked about this formula in the videos. This is just a more general form. This is the probability of the CLR of the outcome. And this is the CLR of not the outcome. And we'll see why this matters. Why. Okay. So this is just a quick example. And let me see. All right. I'm gonna add another slide just in case I need it. All right. Okay. So you have 80% safe drivers and 20% risky drivers. The probability of a safe and risky driver having an accident, 0.5, 0.05, and 0.3. Accidents in each year are independent. So that's just the statement saying that you can do the PA dot P. This holds. And this just makes everything that we're going to be doing using these formulas easier. Accidents are independent. A client has 1 accident in 4 years. What is the likelihood ratio that the person is a risky driver? Right. So essentially, this question is asking you, how likely is the person a risky driver, given their record? So, how to distinguish events and outcomes? Which one arises from which? An outcome must always arise from an event. So, which one arises from which? Accidents arise from driving, right? Not the other way around. So your event is the driving or the driver. And the outcome is accident or no accident. So you have PR, they've given that 0.8. PS 0.2, right? And then you have P accident, right?
Isn't the opposite? 80% are safe. And
oh, thank you, James. Thank you. Great. All right. So 20% are risky drivers and 80% are safe drivers. that is also good for society at large. So in this question, it's saying that if you have an accident, the probability of having an accident, given that you are a safe driver, is 0.05, and the probability that you are a risky driver, that you have an accident given you're a risky driver is higher, 0.3. Okay, now the way this question is framed, given that a client has one accident in 4 years, so LR something given one accident in 1 year, 3 years without accidents, what is the likelihood ratio that the person is a risky driver, right? This is what we are looking for. So the 3 ingredients, LR sub 0, CLR I, CLR J, LR N. These are the 3 things that we need to look for. So first, LR0 is the probability of the event over 1 minus the probability of the event, right? And here the event of concern is risky driver. ER over 1 minus ER, and that's just 2 over 0.8. That's just 0.25. Now, CLR of your outcome, right? Your I, where I and J are outcomes, is the set of all your outcomes. So first I, accident, right? Same as here, probability that you have an accident, given that you're a risky driver, probability that you have an accident, given that you are a safe driver. So because this is the conditional probability of only one outcome, of the outcome of an accident, this bit right here stays the same. This bit right here changes. 2 events, both complementary to each other, given one outcome, right? So this you know it to be 0.05 and 0.3. So 0.3 over 0.05. This is just 6, right? And for likelihood ratios, is okay. This is okay. Because eventually, this is what it's going to give you. Likelihood ratios are your bridge to the probability of a conditional outcome. Oh, sorry, conditional event. Now, we've covered one outcome. We should cover the other outcome. No accident. Given risky driver, no accident, given safe driver. This is just 1 minus R. Right? This goes back to this rule here, partitioning. Right? Rule 1. Because here we consider the event as 2 separate subspaces. So this is the subspace of risky driver, and this is the subspace of safe driver. And in the risky driver subspace, you have 2 outcomes, right? Accident, no accident. Oh, yeah, I'll be sharing this. And in the subspace of the event in which, oh, you're welcome, Aaron. in the subspace in which you have a safe driver, the event of a safe driver. No accident. This is why you have this. The events form their own subspace each. That's the way I like to think of it, at least. This is just 7 over 0.5. And that is just 0.736, right? And then after that, you just plug it all in. LR of the event given these two outcomes. So this is just to reiterate, risky given 1 accident, 3 no accidents, is formula CLRI power 1 or J power 3, where I is accident and J is no accident. Right? And this is just simple arithmetic, and you plug it all in, and then you're going to get 0.60. All right. If you take this one step further, and we ask you probability that you are a risky driver, the event that you are a risky driver, given that your driving record shows that you have 1 accident in 4 years. Right? And this is just, I think this is somewhere about 0.375. So regardless of the magnitude of your likelihood ratio, you are probably never going to see a probability that's more than 1, unless you've done something terribly wrong with your calculation up here. So, any questions? Please feel free to put it in the chat. All right, so I'm going to move on to subjective probability. I'm just going to go over this very quickly. Foxes and hedgehogs. Foxes are basically your jack of all trades. They're a master of none. They know a lot, but shallowly. Hedgehogs are your experts. They dive in to just one topic. They know it deeply, but they're almost entirely ignorant of everything else. That's a hedgehog. And then you have your types of methods of elicitation, your NDM, which relies heavily on the instincts of your experts. And then you have the expert opinion. So basically, if you subscribe by getting your probabilities through NDM, you're just going to take those probabilities and not ask any questions. You're going to be like, okay, you're an expert. I'm going to take your word for it. I'm just going to use these probabilities, no questions asked. It's instinctive, right? Experts will give their expert opinion based off their experience. On the other hand, heuristics and biases, they say that, oh, these experts have biases. We are not going to listen to you. And these biases are caused by your experience, by the information that you're exposed to, by your own, like, what's your agenda kind of thing. So the 4 main biases that are important for the quiz, actually only out of these 4, let's see, only these 2 are important, right? These 2 matter most. So availability bias is basically, you can think about it, one way to think about it would be social media, right? If you're exposed to something a lot over a long period of time, but regardless of whether the thing is true or not, regardless of its statistics, you're going to think that it happens a lot, right? representative bias is basically stereotypes. You see a nerdy kid, the stereotype is, oh, they're going to be a scientist or a doctor or an accountant. You see a sporty kid, they're going to be a basketball player or a coach or something else that's not an accountant. That stereotype of representative bias. Just quickly to go over anchoring bias and motivational bias. Anchoring bias is based off previous experience. And the example I like to use is lottery tickets. If you have previously won the lottery, you will probably buy another ticket thinking that you are likely to win the lottery again because of anchoring bias, because your previous experience has told you that, oh, I can win a lottery. It is possible. Therefore, I buy it again. That's anchoring bias. Don't get confused between anchoring and availability bias. Anchoring bias is based off your own lived-in experience. Availability bias is just how available that information is to you. It doesn't have had to happen to you yet or ever at all. Motivational bias is agenda or the importance you place on certain things or your preferences. I am more likely to choose A over B because I feel like I'm more familiar with A over B. Or a politician will highlight certain issues that they have a personal stake in because they have motivational bias to do so. That's motivational bias. Okay, now, just to go over, we go into expected value of perfect information. This is essentially how much you would pay for perfect information. And this term perfect information is a little bit of, it's a little bit misleading. It's basically how much would you pay for more certainty or higher return, right? So the basic formula is EVPI equals to C minus EMV, where C is the cost of your fortune teller or your expert. New software. Machine learning thingamajig. Right? And C is usually the thing that concerns you the most. What you want to find. All right. So this, I'm just going to go through this example a little quicker because there's a lot going on. So the first thing I want to draw your attention to is that this is market behavior and this is the expert's forecast. So typically in the real world, when you have an expert, you have to pay the expert something, right? When you pay the expert something, it's going to incur cost and it's going to lower your ultimate expected monetary value to that of the original market behavior value. So say hypothetically, your EMV of market behavior is S1000, right? And your EVPI, which is of your expert's forecast, is 1,200. Let's just assume, since I'm a little nervous that we might not have time to go through everything, accounting for questions from you guys as well. So say if you've hired an expert. They're claiming that if you hire them, they can raise your EMV to $1,200. The expected value of that perfect information is $1,200. How much would you be willing to pay that expert, or how much would you be willing to spend on that new technology to bring your expected value up from 1,000 to 1,200? That's your C. Right? And in this case, it's $200. This value here is the max amount you're willing to spend on the forecast, or how much you'd be willing to spend on that new technology. Because usually, I'm gonna draw like one more here, insert.
Just a quick question on that last problem. So the expected value of perfect information is not how much you would pay. It is what the expected value is if you have perfect information.
Correct.
And then how much you would pay is would be a different
Correct.
question. Got it.
Correct. So, okay, just to reiterate that. My English is not working today. So a more clear example would be, this is something that's more common, right? Let's say you have this new test, this new technology to test. I'll test. But if you conduct this new test, it would cost you $200. But success would be raised to 0.9. Neutral, same results would be just 0.3 or 0.02, and fail would be 0.8. Okay, but if you don't do a test, right, you will succeed only 0.5. You're going to be neutral with probability 0.25, and you're going to fail with probability 0.25. Right? If you fail, you lose $100. If you're neutral, you gain nothing. If you succeed, you gain $1,000. Right? Same here. Usually, the question will ask, they won't give you this value, or they'll ask, is it worth doing the test? Right? So if you calculate the expected value here, right? Perfect information. That's going to be right? Say this is not given, but the EMV of no test is 500. That's 450, right? So how much would you be willing to pay for your test? C. So this right here is the max you'd be willing to pay for the test to bring your EMV up to 892. But if the question gives you, say, -200, it can ask you, is it worth doing the test? And in this case, yes, because your C is more than whatever it is the test costs, right? Does that sound like it makes sense to you guys?
Yes, thank you.
Okay, great. Because this is something that people get tripped up on a little bit more than usual. Okay, so if everybody is good with EVPI, I'm going to move on to risk attitudes. So there are 3 risk attitudes. The first being risk seeking, risk neutral, and risk averse. So 1 minute. So they're all defined by 2 things. First, the value of their certainty equivalent minus their EMV. Second, shape of the. So I'll go over number 2 first. Shape of the curve, right? If you are risk averse, I'm going to call this UX. The double derivative is going to be less than 0, right? It's increasing at a slower rate. If you're risk neutral, it's going to be 0, right? Because it's a straight line. If you're risk seeking, the higher the amount that you get in return, the higher the dollar value, the more risk you're willing to take. The faster your gradient, the gradient of your graph changes. If you're risk neutral, your utility increases as the dollar, or I like to think about it as your return on investment, ROI, increases. So the more your ROI increases, the more you're willing to take the risk. But this varies linearly if you're risk neutral. However, if you are risk averse, somebody is gonna have to pay you money to take that initial risk. This value over here is your CE, the certainty equivalent. The amount of money that you're going to have to be paid to be certain that you want to take the risk, to be certain that you're going to get the ROI. Okay. Now, let me clarify something, because this was a question that I got in the on-campus section. Let me clarify this. Okay. Let me add one more. All right. It's easier if I draw it out. If this is your dollar amount and this is your utility, UX, right? And you have this arbitrary curve. If you are, let me make these axes a little shorter so I have space. This is just an arbitrary graph. dollar amount, or your return on investment, or however much you want to think about it, however you want to think about it. Usually, you have your EMV, expected monetary value. And for this given EMV, you have your expected utility, EU. So something that I want to highlight first and foremost is EU should not be confused with EMV. EU takes dollar values and converts them into how useful that dollar value will be to you. EU of EMV is how useful this utility, this EMV is going to be to you based off this utility function. So here you have your EMV. Now, if say you are risk seeking, right? You want your EMV to be higher. This is your expected utility. And this difference here is your risk premium. So there are a couple of new terms here. One, CEE, certainty equivalent, right? The amount of money, how much you need to be paid to take on a risk. Or vice versa, how much you would want to pay to take that risk. So let me double check this with the slides. Okay. I should explain our risk premium. This is basically E minus CE. Right. So I'm going to explain the intuition with this graph. If you are risk seeking, you are more certain than your typical neutral guy that you're going to have a higher return on investment. So you want to take that risk. You are willing to pay to take that risk. You're willing to lose a little bit of money. So that's why your RP, your risk premium, is negative. You're willing to lose a little bit of money to take that risk because you want that risk. You're willing to buy that risk. So it's a cost to you. So RP less than 0. You're buying that risk. If you're risk neutral, basically your EMV equals to your CE, so your risk premium is 0. If you're risk averse, someone will have to buy the risk from you. RP is 0, right? So think about it. So whenever you're paying for insurance, basically, if you think about it in insurance premiums, right? The reason why you're paying them, the reason why it's a cost to you is because insurance companies are treating you as a risk-seeking agent. You're buying the risk to do certain things. You're buying the risk to own a car. You're buying the risk to treat your teeth or to go to the hospital. You're buying that risk and it is a cost to you. However, if you are selling insurance, you are risk averse. You want to protect yourself from risk. So you get someone to buy that risk from you. You're willing to sell your ability to explore, to sort of like basically your options. You're selling options and futures and opportunities for a price, which is why your risk premium is more than zero, which is why insurance companies earn that money, because they're selling that opportunity to you. That is one way to think about it. Does that make sense to everyone? I know that's like a little bit convoluted. Okay, I'm going to assume that it's all okay. All right, great. Okay, so now here I want to draw the distinction between utility functions and EMV, right? This right here is a nonlinear UX. You are taking your dollar value and transforming it to some use to you in a nonlinear way. So for this particular investor, the utility of 15,000 is right. So that is it's not the same as the EMV. So I'm only going to go through this very quickly because we still have a couple more slides after this. But I just want to draw the distinction between utility and EMV. Your expected utility is going to be and so on. This is your expected utility. This is an example of a non-linear utility function. An example of a linear utility function is where and x minus is just the worst outcome and x plus is the best outcome. So this is a normalization of dollar value to utility. This is a linear UX. Same thing, sub it back in here to calculate your overall expected utility. So far, so good. You do the same thing, you draw a decision tree. The only difference now is instead of directly calculating ENV, just multiplying all those probabilities of dollar values, you're multiplying probabilities with the expected utility value that you derive using your utility function. So instead of P times dollar value, it'll be P times utility of X to get your expected utility. So if that makes sense, I'll move on to utility paradoxes. So this is just the ones that really matter are ordering and transitivity, substitutability. Yeah, these two. Let me double check. Okay. So transitivity. basically means if I prefer option 1 to option 2 and option 2 to option 3, I automatically prefer option 1 to option 3. That's transitivity. Okay. And then for reduction, it's just, this is your aversion to ambiguity. You can think about it as aversion to ambiguity. It basically says that a perfectly logical decision maker will not worry about how complicated the probabilities are. All they care about is the EMV. It doesn't matter how many loops of conditional probability they have to jump through, how much risk they have to take. Only the expected monetary value matters. And then let's see. Continuity is a little more confusing. It basically says that let me take a look at this. If you have one outcome, one desirable outcome C, very desirable, you can find some combination of two other outcomes, C1 and C2, that are less desirable, but give you the same expected monetary value. Substitutability is something that you've probably heard of before. It's saying that substitutability. Right. If you have an event E, but you substitute event E with two events, E1 and E2, that are less certain, but the total probability adds up to 1, right? And the EMV of E1 and E2 are the same as E. A rational decision maker. To a rational decision maker, E is the same, sorry, the EMV, sorry, they'll prefer, preference of E is going to be the preference of the combination of E1 and E2 together. That's substitutability. You can substitute two uncertain events for one certain event. And then monotonicity. Right here, let me change the color a bit. Basically, it's similar to reduction, but we're not considering ambiguity here. We're not considering aversion to ambiguity. This is purely the same. This only has to do with two things: possible outcomes and EMV. So monotonicity says that if I have two separate outcomes, two events in which those two events will give me the same outcomes, I'm going to prefer them. I'm going to prefer the one with the higher probability of winning the preferred outcome, or the higher probability. Yeah, so let me draw this out a little bit. If I have event A and event B, and event A gives me $50 with 0.8 and $1,000 with 0.2. It gives me 50 with 0.8 say 1 and 1000 it's 0.9. A perfectly rational decision maker following monotonicity will want to choose B. That's monotonicity. And then you also have finiteness, which is there's nothing infinitely bad or infinitely good. Oh, I'm not sure what happened. Use my funky iPad. Okay, we're back. Are we back? Oh, please. Great, we're back. All right. Finiteness. There's
We
nothing
still can't.
infinitely good or bad.
We still can't see it.
Oh. Okay, that's okay. So without the examples, without the PowerPoint, I just want to mention the two paradoxes that you should be paying attention to are the LAs and also Ellsberg. So the LA paradox basically is a violation of the invariance axiom. And it says it's usually caused by human irrationality. So it says that if I prefer choice 1 over choice 2 and choice 2 over choice 3, it does not mean that I prefer choice 1 over choice 3. That's LA. Ellsberg is caused by ambiguity aversion, which is your axiom number 2, reduction of compound uncertain events. So Ellsberg is caused by violation of that second axiom. Ellsberg's paradox basically says that people fixate on what they have available, and if they're uncertain about something, they immediately don't want to do it, or they don't want to take the risk. So I think that about wraps up our review. I will be sending out the recording of this, and I will also be sending out the PowerPoint presentation for this. Does anyone have questions about the quiz overall?
Oh, thank you for doing this, though.
Thank you.
Yeah, no problem.
Thank you.
All right, you're welcome.
Bye.
Bye, good luck for tomorrow.